All right, let's take a look at example number 1. So this example asks us to use bond energies to determine the heat of a reaction for the complete combustion of methane. So we've been given methane. We know that methane is CH4. Oops. So I'm just going to write my reaction out first, and then we can go from there. So CH4 plus O2, which is oxygen, right? That's what combustion is. And complete combustion tells me that the products are CO2 gas plus H2O gas. The first thing that I want to do is balance this reaction, right? If I don't balance it, my answer is going to be completely wrong. When I balance it, I am going to first take a look at my carbons. There's 1 and 1. Looking at my hydrogens, I've got 4 on the left side and 2 on the right side, so I'm going to put a 2 here. And in order to balance out the oxygens, I'm going to put a 2 here. So I have my complete combustion reaction all balanced. Now my next step, because I know we're using bond energies, I have to draw out these structures. I know that CH4 is going to look like this, so C surrounded by 4 single bonds with hydrogen, plus I know that O2 is going to be 2 oxygens bonded together. Each one has 2 lone pairs. Carbon dioxide, there's carbon in the center, 2 oxygens on either side. Each oxygen has 2 lone pairs, plus water. Looks like this, right? So I just drew one of each molecule. Now what I'm going to do is just write the coefficients of each of these right next to each other. And this is just because we're doing our first example. I'm spending a little bit more time drawing these structures, writing the coefficients out, being a little bit more detailed, and that does take a bit more time. I just want you to see the full step for all of these, right? Eventually, when we get into the practice problems, you can be a lot quicker with these. And when you're drawing out these structures, if you know what those structures look like and you know what the lone pairs are, then it's okay to omit those in these specific scenarios, right? Because the only reason for us drawing these out is to take a look at what type of bonds there are so that we can find the bond energies. Okay, our delta H, I'm not going to write the formula out, but we're going to start by taking a look at the total energy of the bonds broken. So bonds broken tells me that we're looking at our reactants. So let's start with CH4. Lucky for us, there's only one type of bond in CH4. So I'm going to start with the coefficient. The coefficient here is 1. So 1 mole times, there are 4 different CH4 bonds there, times the bond energy of CH, right? That's the bond that we're looking at right now, 413 kilojoules per mole. Okay, so I've done CH4. Now I'm going to move on to O2. So first of all, coefficient, I know that there are 2 moles of O2, and there's only one double bond here between the 2 oxygens, right? So I'm just going to write the number 1 times, looking at the bond energy for O2, or when 2 oxygens are double bonded to each other, that would be 495 kilojoules per mole. And you can see that because I've accounted for my coefficients, my units of the moles can cancel out. So now I've looked at the total energy of the bonds broken. Now we're going to take a look at the total energy of the bonds formed. So starting with CO2. So I know that the coefficient here is 1. So I know that there's 1 mole times, if I take a look at this particular molecule, there are 2 different C double bond O bonds. C double bond O bonds. So I'm going to put the number 2 there, right? So this is 1 and this is 2. Times the bond energy associated with a carbon double bonded to an oxygen. Now, this is that scenario where usually it's 745 kilojoules per mole, but because we're looking at carbon dioxide, it is going to be 799 kilojoules per mole. And my moles will cancel out, plus 2 times the H2O, right? So 2 moles of H2O times, there are 2 OH bonds, times the bond energy required for this OH bond is 467 kilojoules per mole. Kilojoules per mole. Close off this bracket. My moles will cancel out. Okay, so if I sum up the total energy of the bonds broken, it is going to be 2642 kilojoules. Right, and I got that by adding up this value to this value. And when I add up all of the energy of the bonds formed, it is going to be 3466 kilojoules. Notice that the units for both of these are kilojoules because anytime you had kilojoules per mole, you multiplied by that coefficient, so that mole is now canceled out. When you add those two numbers up, or rather subtract these two numbers, you are going to get negative 824 kilojoules. So that is the delta H for the complete combustion of methane. Oops.